English sentence is divided into 3 parts, just like hamburger.
Oh, nothing's easy this morning. This is MVLink, and it goes across the entire back spine of a rack of GPUs. And these GPUs are all connected, 72 dual GPU packages of Blackwell's, 144 GPUs, connected together so it's one giant GPU. General purpose computing as we know it has existed for 60 years, until now. For the last 30 years, we've had the benefit of Moore's Law, an incredible phenomenon. Without changing the software, the hardware can continue to improve in an architecturally compatible way. Every single industry has subsequently been built on top of it, but we know now that the scaling of CPUs has reached its limit. The free ride of Moore's Law has ended. We no longer can afford to do nothing in software and expect that our computing experience will continue to improve, that costs will decrease, and continue to spread the benefits of IT and to benefit from solving greater and greater challenges. We started our company to accelerate software. Our vision was there are applications that would benefit from acceleration. That acceleration benefit has the same qualities as Moore's Law. For applications that were impossible or impractical to perform using general purpose computing, we have the benefits of accelerated computing to realize that capability. For example, computer graphics. Real-time computer graphics was made possible because of Nvidia coming into the world and make possible this new processor we call GPUs. But we felt that long-term, accelerated computing could be far, far more impactful. There is no such magical processor that can accelerate everything in the world. Because if you could do that, you would just call it a CPU. You need to reinvent the computing stack from the algorithms to the architecture underneath and connect it to applications on top. In one domain after another domain, computer graphics is a beginning, but we've taken this CUDA architecture from one industry after another industry after another industry. Today, we accelerate so many important industries. cuLitho is fundamental to semiconductor manufacturing, computational lithography, simulation, computer-aided engineering, quantum computing, so that we can invent the future of computing with classical, quantum, hybrid computing. In each one of these different libraries, we're able to accelerate the application 20, 30, 50 times. Of course, it takes a rewrite of software, which is the reason why it's taken so long. In each one of these domains, we've had to work with the industry, work with our ecosystem, software developers and customers, in order to accelerate those applications for their domains. Modulus, teaching an AI the laws of physics, not just to be able to predict next word, but to be able to predict the next moment in time of fluid dynamics and particle physics and so on and so forth. And of course, one of the most famous application libraries we've ever created, called cuDNN, made it possible to democratize artificial intelligence as we know it. These acceleration libraries now cover so many different domains that it appears that accelerated computing is used everywhere. But that's simply because we've applied this architecture, one domain after another domain, that we've covered just about every single industry. Now, accelerated computing, or CUDA, has reached the tipping point. The first thing that happened, of course, is how we do software. Our industry is underpinned by the method by which software is done. The way that software was done, call it software 1.0, programmers would code algorithms, we call functions, to run on a computer. And we would apply it to input information to predict an output. Somebody would write Python or C or Fortran or Pascal or C++, code algorithms that run on a computer. You apply input to it, and output is produced. very classically, the computer model that we understood quite well. However, that approach of developing software has been disrupted. It is now not coding, but machine learning. Using a computer to study the patterns and relationships of massive amounts of observed data to essentially learn from it the function that predicts it. And so we are essentially designing a universal function approximator using machines to learn the expected output that would produce such a function. And so going back and forth, looking, this is software 1.0 with human coding to now software 2.0 using machine learning. Notice who is writing the software. The software is now written by the computer. And after you're done training the model, you inference the model. You then apply that function now as the input. That deep learning model, that computer vision model, speech understanding model, is now an input neural network that goes into the GPU that can now make a prediction given new input, unobserved input. And we have gone from coding to machine learning, from developing software to creating artificial intelligence, and from software that prefers to run on CPUs to now neural networks that runs best on GPUs. This, at its core, is what happened to our industry in the last 10 years. We have now seen the complete reinvention of the computing stack. The whole technology stack has been reinvented. The hardware, the way that software is developed, and what software can do is now fundamentally different. We dedicated ourselves to advance this field. And so this is what we now build. Initially, we were building GPUs that fit into a PCI Express card that goes into your PC. This is what a GPU looks like today. This is Blackwell. Yeah, thank you. A massive system designed to study data at an enormous scale so that we could discover patterns and relationships and learn the meaning of the data. This is the Greek breakthrough. In the last several years, we have now learned the representation or the meaning of words and numbers and images and pixels and videos, chemicals, proteins, amino acids, fluid patterns, particle physics. We have now learned the meaning of so many different types of data. We have learned to represent information in so many different modalities. Not only have we learned the meaning of it, we can translate it to another modality. So one great example, of course, is translating English to Hindi. Translating English, large body of text, into other English, summarization, from pixels to image recognition, from words to pixels, image generation, from images, videos, to words, captioning, from words to proteins used for drug discovery, from words to chemicals, discovering new compounds, all because of this one instrument that made it possible for us to study data at enormous scales. Well, I just want to say that in order to build the Blackwell system, of course the Blackwell GPU is involved, but it takes 7 other chips. TSMC manufacture all of these chips, and they're just doing an extraordinary job ramping the Blackwell system. Blackwell is in full production, and we're expecting to deliver in volume production in Q4. And so this is basically Blackwell. Now this is one of the things that's really incredible about the system. Let me show it to you. Oh, nothing's easy this morning. This is MVLink, and it goes across the entire back spine of a rack of GPUs. And these GPUs are all connected 72 dual GPU packages of Blackwells, 144 GPUs, connected together so it's one giant GPU. If I were to spread out all of the chips to show you what this connects together, it's essentially a GPU so large, it'd be like this big. But it's obviously impossible to build GPUs that large, so we break it up into the smallest chunks we could, which is reticle limits and the most advanced technologies, and we connect it together using MVLink. This is MVLink backspine. You're looking at all of the GPUs being connected. That's the quantum switch that connects all of these GPUs together on top. Spectrum-X, if you would like to have Ethernet. What connects this together, this is connected to this switch, and this is one of the most advanced switches the world's ever built. Now, all of this together represents Blackwell, and then it runs the software that's on top. The CUDA software, cuDNN software, Megatron for training the large language models, TensorRT for doing the inference, TensorRT LLM for doing distributed multi-GPU inference for large language models. And then on top of that, we have two software stacks. One is Nvidia AI Enterprise that I'll talk about in a second, and then the other is Omniverse. So this is the Blackwell system. This is what Nvidia builds today. Of course, the computation is incredible. Each rack is 3,000 pounds, 120 kilowatts, 120,000 watts in each rack. The density of computing, the highest the world's ever known. And what we're trying to do is to learn larger and smarter models. Each year, we're increasing the amount of data and the model size each by about a factor of 2, which means that every single year, the computation, which is the product of those two, has to increase by a factor of 4. Now remember, there was a time when the world, Moore's law was 2 times every year and a half, or 10 times every 5 years, 100 times every 10 years. We are now moving technology at a rate of 4 times every year. 4 times every year over the course of 10 years, incredible scaling. The second thing that we've discovered recently, and this is a very big deal, intelligence is not just one shot, but intelligence requires thinking. And thinking is reasoning, and maybe you're doing path planning, and maybe you're doing some simulations in your mind. You're reflecting on your own answers. And so as a result, thinking results in higher quality answers. And we've now discovered a second scaling law. And this is a scaling law at a time of inference. The longer you think, the higher quality answer you can produce. This is not illogical. This is very intuitive to all of us. If you were to ask me, what's my favorite Indian food, I would tell you chicken biryani. Okay? And I don't have to think about that very much, and I don't have to reason about that. I just know it. And there are many things that you can ask it. Like, for example, what's NVIDIA good at? NVIDIA is good at building AI supercomputers. NVIDIA is great at building GPUs. And those are things that you know that it's encoded into your knowledge. However, there are many things that requires reasoning. For example, if I had to travel from Mumbai to California, I want to do it in a way that allows me to enjoy 4 other cities along the way. If I were to tell it, I would like to go from California to Mumbai. I would like to do it within 3 days. And I give it all kinds of constraints about what time I'm willing to leave and able to leave, what hotels I like to stay at, so on and so forth, the people I have to meet. The number of permutations of that, of course, quite high. And so the planning of that process, coming up with an optimal plan, is very, very complicated. And so that's where thinking, reasoning, planning comes in. And the more you compute, the higher quality answer you could provide. And so we now have 2 fundamental scaling laws that is driving our technology development. First for training, and now for inference. The number of foundation model makers has more than doubled since the beginning of Hopper. There are more companies that realize that fundamental intelligence is vital to their company, and that they have to build foundation model technology. And second, the size of the models have increased by 20, 30, 40x the amount of computation necessary to train these models because of the size of the models, but also multimodality capability, reinforcement learning capability, synthetic data generation capability. The amount of data that we use to train these models has really grown tremendously. That's one, and then the other reason, of course, is that Blackwell is also used for generating tokens at incredible speeds. And so together, all of these factors has led to the demand for Blackwell being incredibly high. Let's talk about now how we're going to use this technology. Earlier I told you that we have Blackwell, we have all of the libraries, acceleration libraries that we were talking about before, but on top there are two very important platforms we're working on. One of them is called Nvidia AI Enterprise, and the other is called Nvidia Omniverse, and I'll explain each one of them very quickly. First, Nvidia AI Enterprise. This is a time now where the large language models and the fundamental AI capabilities have reached a level of capabilities we're able to now create what is called agents. Large language models that understand the data that, of course, is being presented. It could be streaming data, it could be video data, language model data, it could be data of all kinds. The first stage is perception. The second is reasoning about, given its observations, what is the mission and what is the task it has to perform. In order to perform that task, the agent would break down that task into steps of other tasks. And it would reason about what it would take, and it would connect with other AI models. Maybe it's a model that understands how to generate images. Maybe it's a model that is able to retrieve AI semantic data from a proprietary database. So each one of these large language models are connected to the central reasoning large language model we call agent. And so these agents are able to perform all kinds of tasks. Some of them are maybe marketing agents, some of them are customer service agents, some of them are chip design agents. Nvidia has chip design agents all over our company helping us design chips. And so we're going to have agents that are helping our employees become super employees. These agents, or agentic AI models, augment all of our employees to supercharge them, make them more productive. Now, when you think about these agents, it's really the way you would bring these agents into your company is not unlike the way you would onboard someone who's a new employee. You have to give them training curriculum, you evaluate them, and so there are evaluation systems, and you might guardrail them. If you're an accounting agent, don't do marketing. And so each one of these agents are guardrailed. That entire process we put into essentially an agent lifecycle suite of libraries. And so this is what we call NVIDIA NeMo. We have, on the one hand, the libraries. On the other hand, what comes out of the output of it is an API inference microservice we call NIMS. Essentially, this is a factory that builds AIs. And NeMo is a suite of libraries that onboard and help you operate the AIs. And ultimately, your goal is to create a whole bunch of agents. The next generation of IT is going to be about producing and delivery of AI. And as you know, the delivery of software, coding, and the delivery of AI is fundamentally different, but dramatically more impactful, insanely more exciting. The second part is this: what happens after agents? Now remember, every single company has employees, but most companies, the goal is to build something, to produce something, to make something. It could be factories, it could be warehouses, it could be cars and planes and trains and ships, all kinds of things. That next generation of AI needs to understand the physical world. We call it physical AI. In order to create physical AI, we need 3 computers. And we created 3 computers to do so. The DGX computer, which Blackwell, for example, is a reference design, an architecture to create things like DGX computers for training the model. That model needs a place to be refined. It needs a place to learn. It needs the place to apply its physical capability, its robotics capability. We call that Omniverse, a virtual world that obeys the laws of physics, where robots can learn to be robots. And then when you're done with the training of it, that AI model could then run in the actual robotic system. That robotic system could be a car, it could be a robot, it could be it could be a autonomous moving robot, it could be a picking arm, it could be an entire factory or an entire warehouse that's robotic. And that computer we call AGX, Jetson AGX, DGX for training, and then Omniverse for doing the digital twin. Start locally, grow globally.
Right.
Right, that's fantastic. Okay.
Thank you. Thank you.
Thank you very much, Michelle.
Thank you.
Thank you.